So students, let's talk about water. It's the most important molecule that exists in the human body, probably the most important molecule that exists in the universe. And almost every class, whether it's a biology class or in this case a biochemistry class, usually starts off with water. So I'm going to go over 7 or 8 critical points. You can expand on that using your lecture notes, your PowerPoint notes, also the notes that I have printed out and given to you on the first day of class. So this is just a very quick review. I'm going to go over some bullet points, but for each bullet point, make sure you know and can expand on those bullet points for the exam and in your head. But I'm just going to go over this very fast for the sake of brevity. Alright, so some of the important qualities and characteristics of water. First and foremost, water is a polar molecule that has a bent Lewis structure. So if you remember the structure of water, it actually has 2 lone pairs on the oxygen, and those 2 lone pairs of electrons on the oxygen atom actually give the molecule a bent geometry. Okay, so instead of water being a linear molecule, which is what we would expect, H, O, and H sort of at a 180-degree bond angle, a straight line, the geometry is not like that. Okay, those 2 lone pairs of electrons on the oxygen atom distort the molecule and give it a bent shape. Okay, so a polar molecule that has a bent geometry, this is a covalent bond, and a covalent bond here. So instead of calling water a polar molecule, we can call it a polar covalent molecule, or a molecule that has a polar covalent bond, if we want to get really technical. And the relevance of that, the importance of that, is manyfold. Okay, one of the things that we know about polar molecules, if you remember from general chemistry, is this concept of a dipole moment. So this covalent bond between this hydrogen and that oxygen has an unequal electron distribution. The electron distribution favors the oxygen atom, so that the oxygen atom has a partial negative charge, leaving this hydrogen as a partial positive charge. So that is the net dipole moment of electron density moving towards the oxygen. Same thing occurs for this hydrogen here. And so this hydrogen, okay, gets a lot of its electron density sucked away into this oxygen atom. So the electron density or the electronegativity is pulled towards the oxygen atom, giving this oxygen atom a partial negative charge and leaving this hydrogen with a partial positive charge. So the net effect of all of this is that water, the water molecule, is not an ionic molecule. There's no real charge transfer. There's no real electron transfer, but you have within it regions of the molecule that have a partial negative charge within the molecule, and you have regions within the molecule that have a partial positive charge. Okay, so that is one critical characteristic, and that confers upon the water molecule a number of distinctive properties. Okay, one of the things that the water molecule does have is a very unique bond angle. So the bond angle of the water molecule, and this is an approximation, I don't know the exact angle off the top of my head, but I think it's about 104 degrees. Again, I do not know the exact bond angle, but the angle between this H and that O and that H is about 104 or so degrees, and that bond angle is unique. Okay, so a very unique bond angle for the water molecule implies some unique characteristics and unique properties of it. So a unique bond angle resulting from the bent geometry. Okay, so water molecule has a bent geometry. It's not a linear molecule. The molecule is bent, HOH, in this bent configuration, giving a bond angle of about 104 degrees or so. All right, so a unique bond angle. As a result of that unique bond angle, we have a number of important characteristics. Okay, unique bond angle and the bent geometry. It's a polar molecule, so water molecules have a region that's negatively charged, as I said before, and regions that are positively charged. So due to that, water can do a number of things, and you probably have already have heard about this from previous introductory science courses, but it's worth mentioning again, the hydrogen bond. Okay, so hydrogen bonding is very crucial and critical for the water molecule, and you'll find it in this class, in this introductory biochemistry class, that water is going to participate in reactions by virtue or stabilize three-dimensional structures of molecules by virtue of its hydrogen bonding capacity. Now, water can also participate in chemical reactions due to its acidic and basic nature. That's the other property we'll allude to a little bit later. But let's think about our functional groups in organic chemistry. Okay, the groups that we have studied, or we will study, that we know are going to be part of biomolecules. Okay. These include alcohols, okay, so water can hydrogen bond with an alcohol. Ketones, ketones have this functional group, so water can hydrogen bond with ketones. Okay, so atoms that have a nitrogen. Okay, so a lot of molecules in our cell will have the nitrogen atom. So amino groups, amines. Okay, water can hydrogen bond with those. Okay, so it's very important to realize that if you have a nitrogen, okay, any part of the molecule, here's the R group, it's a generic group. If you have an oxygen and any part of the molecule, if you have a fluorine, though fluorine is not really seen a lot in biochemistry. If you have any part of the molecule, ketones, alcohols, have nitrogens and oxygens, what happens is that water can participate in a hydrogen bond with them. Okay, so you have to remember what is a hydrogen bond. Okay, it's a very strong interaction between one part of a molecule that has a nitrogen, oxygen, or fluorine, and the hydrogen, the partial positive charge of a hydrogen in a water molecule. So remember, this hydrogen will have a partial positive charge in this water molecule. This nitrogen somewhere in a protein or any type of biomolecule will have a partial negative charge. Same thing with this oxygen, same thing with this fluorine. Okay, this oxygen in the water molecule will have a partial negative charge, and then this hydrogen will have a partial positive charge. So partial positive will interact with a partial negative. Okay. So these can be found in ketones, these can be found in alcohols, these can be found in amine groups. All right. Sometimes sulfur gets added into the mix, but for now we'll just worry about nitrogen, oxygen, and fluorine. Nitrogen and oxygen are definitely going to participate in a hydrogen bond. All right. So those are the functional groups that a hydrogen bond can occur, but probably already know that water can hydrogen bond to itself. All right. So when water hydrogen bonds to itself, we get a very intricate network of water molecules. And ice, the ice that's in ice water is nothing more than a lattice of hydrogen bonds, okay, where the partial negative of one oxygen atom in the water molecule will have a positive electrostatic interaction with the partial the partial negative of the oxygen atom will have an electrostatic interaction with the partial positive of a hydrogen atom of another water molecule situated at some distance away. So like that, your water molecule, if we were going to focus on this water molecule here, all the electron density is focused on the oxygen, giving it a partial negative characteristic. That partial negative characteristic can interact with the partial positive characteristic of another water molecule. Okay, so this is the basis for water molecule interacting and hydrogen bonding to itself, okay, to another molecule of itself. And that is how we get a lattice network of hydrogen bonds, which makes the water molecule, when it's hydrogen bonded to itself, it gives it a very strong intermolecular interaction. Okay, so in terms of biochemistry, that can be exploited to stabilize three-dimensional molecules. You're going to have to start thinking about molecules as being three-dimensional entities and having a three-dimensional structure, and what are the stabilizing forces that drive that stabilization. Okay? And one of the things that drives that stabilization is hydrogen bonding. Not just water to itself, but water to maybe an amino group that's found in a protein, or a hydroxyl group that's found in a carbohydrate. So hydrogen bonding is going to be very important when we talk about how molecules achieve a three-dimensional structure, a stable three-dimensional structure. All right? So hydrogen bonding is a very important property. A couple of other important properties is the ability of water to establish a hydrophobic effect. This is also very important. Because, again, water is a polar molecule. It has partial negative within the molecule with the oxygen and partial positive within that same molecule. As we said before, that would interact with a molecule, another polar molecule. So this partial negative will interact with a partial positive of another molecule. It could be another water molecule, or it could be a totally different molecule. What would you imagine would happen if you have a hydrophobic group, such as a benzene group? Okay, this would be a part of amino acids, which we'll talk about later in the course. Or a molecule that has this alkyl group side chain. Okay, or a molecule that has maybe a double bond associated with it. What type of interaction would have established or be established with this polar water molecule and these water molecules, and these molecules that are hydrophobic? Okay, so let me say that question again. What type of interaction would you expect to see between this polar water molecule and molecules that have hydrophobic moieties, such as a benzene group or an alkyl chain, what type of interaction would it be? Would it be a positive interaction or a negative interaction? Well, from organic chemistry, you should know that these guys probably do not interact with one another so assiduously. Okay, so they are averse. A hydrophobic molecule would, as per its name, or hydrophobic groups would be averse to interacting with water. So what actually would happen is that these would rather interact with themselves than interact with the water molecule. So the effect of all of this is that many times you'll have what's called hydrophobic collapse. And that's how phospholipids, your phospholipid bilayer forms, okay, in the cell membranes that you may have talked about in Biology 1, the phospholipid bilayer, okay. That's self-aggregation of hydrophobic moieties interacting with themselves actually excludes water. So the water, by virtue of its charged components within the molecule, causes hydrophobic patches or hydrophobic regions or hydrophobic functional groups to exclude that water. Okay, so this can have very good consequences if you want to fold a protein, which we'll talk about in this course. It could have also some deleterious consequences as well, because hydrophobic interaction can cause aggregation. So it can be the impetus to cause aggregation, and a lot of diseases result from proteins aggregating or stacking against each other, and they aggregate so much that they essentially precipitate out of your cell. But if you're talking about maybe a molecule that has a three-dimensional structure that looks like that, the interior would consist of what? The interior would consist of hydrophobic regions, while the exterior, which is exposed to the cytoplasm, would probably be and essentially exposed to water. The exterior would have polar groups, polar functional groups, like your alcohols or amines or ketones. They would be exposed to the outside where water is located. So to go to here, a three-dimensional structure of a molecule, okay, which was originally maybe something like that, the hydrophobic effect or hydrophobic collapse, due to these functional groups hating water so much that it will actually be thermodynamically more favorable for this to establish a three-dimensional structure that looks like this, where the hydrophobic groups are excluded from water and are at the interior, while the polar groups would be exposed to the exterior, which is the cytoplasm, which is mostly where water is at. All right, so that's a very powerful effect, the hydrophobic effect, and that again is due to the nature of water. It's worth mentioning here that water is about 70% of your cellular constituents. So when we think of our typical cell, 70% or so of that, as a educated estimate, is water. Okay, so your cytoplasm is essentially water. All the reactions, all the metabolisms are occurring in water. The cytoplasmic soup is water. So yes, if you have a molecule, whether it is a protein or whether it is a glucose molecule or a long chain of sugars, it's going to fold so that its hydrophobic patches or interiors are going to be on the inside, and all the polar moieties or the polar groups are going to be on the outside. So molecules don't look like this. Okay, they spontaneously and thermodynamically favor a structure whose hydrophobic groups are on the inside and whose polar groups are on the outside. A couple of other things, and then we will end it. Water is amphoteric. Okay, so amphoteric is just a fancy word meaning that it has polar qualities and nonpolar qualities. Okay, so it can be both polar and nonpolar within the molecule. The final thing is acid-base reactions. Okay, your pH and pOH come from water. Okay, the ability of acids to protonate water, or the ability of bases to take a proton away from water. So this reaction of H2O, okay, kind of water behaving like an acid and a base. So here, amphoteric, polar and nonpolar qualities. We can also say water has acid-base qualities. Okay. So here, this water molecule donates a proton to become H3O+. And in this course, I usually abbreviate this as H+. Now, once this water donates its proton to make this one H3O+, this H2O becomes OH-. So this reaction is in equilibrium. It has an equilibrium constant of 1.00 times 10 to the minus 14. So even though I have this as an equilibrium, because it's 10 to the minus 14, the reaction actually favors the reactant side. The reaction actually favors left. So very little water molecules actually dissociate to H3O+ and OH-. If you want to take this further, for every 10 to the 14 molecules of water, one molecule of water will actually go and proceed in the forward reaction towards the right and generate hydroxide ion and hydromonium ion. So the bottom line is that while this reaction occurs, it is very negligible. Okay. However, it's enough for us to tell us that water can be a source of acid and water can be a source of base. Okay. So water will participate in reactions in the cell, and water will participate as an acid or as a base. Now, inside the cell, you have a different environment than what's outside the cell. So you will see when we start talking about enzyme mechanisms, and when we start talking about other phenomenon, transporters and reactions, metabolic reactions, mechanisms of metabolic reactions, you'll see that water will participate in that reaction by giving away an acid, or by giving away and being a source of a base. So outside the cell, this is very negligible. Inside the cell, we have proteins and you have all these other constituents. This reaction may become important. Okay, so just to complete this, the equilibrium constant is nothing more than the products over the reactants. All right, but we don't add H2O because it's a liquid. Okay, liquids and solids do not go into our equilibrium constant. And if we further extend our calculations, we'll find that pH is nothing more than minus the log of the hydrogen ion concentration. Okay, pOH is minus the log of the OH concentration. So this pH, which is a measure of acidity, okay, is directly related to the H3O plus concentration, or the H plus concentration resulted from water dissociation. Okay. So for example, the pH of blood will be about 7.4. Okay, what does that mean? The pH of blood is 7.4. It means your hydrogen ion concentration has a pH of 7.4. All right. pH of gastric juice 1.5. Okay, we have an acidic environment. Again, the pH, which is minus the log of the H concentration of H plus, is 1.5, and that comes from water being a source of a proton. Okay, so water is everywhere. All right. pH of household ammonia, used to clean or as a cleansing agent. It's about 12. Okay. So different pHs reflect different concentrations of the hydrogen ion, which, again, because all of this is in water, reflect the capability of water of being an acid. And within our body, we have regions that are kind of neutral in pH, and then we have regions that are very acidic in pH. Physiologic pH is about 7.4 or so. Okay, the pH of a typical cell, okay, in a typical environment. A non-differentiated cell would have a physiologic pH of about 7.4. Right. So those are the basic characteristics of water. Okay, it's a bent polar molecule that has a unique bond angle that facilitates hydrogen bonding with many functional groups that will be found in the cell, such as ketones, hydroxyl groups, so alcohols, primary, secondary, tertiary alcohols, amino groups, primary, secondary, tertiary amino groups, hydrogen bonding with those functional groups, hydrogen bonding with itself, participating in reactions, water being sort of having this duality of acid-base and polar and nonpolar qualities, water being a source for the calculation of pH, which is a measurement of the acidity of substances that are within water. Water is the universal solvent, and everything that life proceeds from emanates or requires water. And there's no more an important molecule in biochemistry than the water molecule. So take some time to look at the PowerPoint notes as well as the notes that I sent out in class. This is just a very brief bullet point overview. Should be able to expand on this for the course as well as for any other exam. By the way, water is so important, it is the source behind MRI, magnetic resonance imaging. So water molecule, which we will not talk about, is actually magnetic. That water molecule can serve as a magnet, orient itself within a magnetic field, and that's used by clinical radiologists to image tissue. So if you are getting it or undergoing an MRI, you're actually imaging water density based on the ability of water to orient in a magnetic field and serve as a contrast between water and tissue, or water and fat, actually. So water is very important. Some key attributes to that, make sure you know this. These attributes, make sure you know these characteristics, and we will definitely talk more about this if we have not already during a class. It's one of the first things we actually cover when we begin Biochemistry 1. So thank you, and do not forget to study in much more greater depth than I've gone over the properties and characteristics of the water molecule.